Hello guys, welcome back to my channel Gamma Die Gamma. So in the previous video, I believe we concluded our discussion or whatever we had to discuss about tensors. In this video, I thought about starting a new topic of Dirac Delta functions. It's a really useful idea across math and physics. So let's get started. Consider the following, and this is sort of an introduction slash motivation page. Assume you have the graph of momentum versus time, and assuming there's some car undergoing some motion. So like the graph, it sort of looks like this, where it starts its increase in momentum at time t1, stops increasing t2, and then consider this vertical value to be change in momentum delta of m naught v. We're assuming the mass is v, is m naught. Okay. Now on the other hand, for the same scenario, consider a force versus a time graph. So we can represent the same motion that's going on, except we just mapping out force versus time. So for the same motion, we're gonna have something like this. Again, apologies for the freehand crude drawing. And the area under the curve is going to be delta m naught v. So what was the perpendicular height is now the area. Because we just graph different entities, at least in the vertical axis. So this area that I've shaded out, that's basically going to be delta of m naught v. So say this is like t1, that's like t2. In general, this change in momentum is always going to be gradual. It's never going to be completely steep, because think about it this way: it takes some time for, say, a car to go from 0 to say 40 kilometers per hour. We're going to require some finite amount of time. The impulse is basically this change in momentum value, is delta m naught v value, which is just the area under this curve in the second graph. So for the case of an ideal impulse, you see this time period of change where the change occurs, it's t1, t2, which I claimed is always finite for like real world situations. Well, we're going to let that time period go to 0 for an ideal impulse. So for an ideal impulse, and this is again hypothetical, we're going to have something like this, and then like an extremely steep change, and again sort of this perpendicular value is delta m naught v. At just one point, because this interval basically just squeezed together to get one point. This is momentum versus time. Okay, and let's do the same. denote the same scenario, hypothetical scenario, with the force versus time graph, which is going to be pretty strange. So if you kind of notice what I did here, I sort of squeezed this T1 and T2 sort of together, and when I do that, this graph basically becomes this, like, sort of a one part of this square wave. If I do the same in the second graph, I'm gonna get this peak to be sort of sharper and sharper at that one point T0. So it's gonna have basically a base that's going to 0 and a height that's increasing because we have to maintain the same area. So it's gonna look something like this. It's gonna be really narrow. That's why I'm drawing one straight line instead of something with like two lines. And infinite height. Think about it this way, because we shrunk down the base to 0, the height had to increase to maintain the same area. Because again, we want the area of this guy to be delta m naught v. You might say this is a clearly hypothetical situation, because having a height of infinity for a base 0, well, it's not even like a real function. It's like it's a divergence going on there. It's clearly blowing up at that point T0. And again, it's 0 everywhere else. So to summarize all that we did on top, consider this region, say T minus, and this region T plus. Integral from T minus to T plus. T minus is all, say, from negative infinity to T0, and T plus is T0 to positive infinity. The integral f of t dt, we want that because of basically the physical significance of what's going on in the case of an ideal impulse. Delta m naught v, if T0 is included in this range, and 0 otherwise. If, say, T0 is not a point in the domain in this or whatever range, it does not even have to be the domain, it can be a subset of the domain. If T0 is not in that subset, it's all going to be 0, right? Because we have a specific time value for where the force is sort of infinite because we're not giving it enough time to sort of gradually increase, like in what happens in the real world. We're just increasing it like out of the blue. So as I said, it seems quite hypothetical that there's this like infinite force going on over an interval that's sort of going to 0. So we have this situation, but we need to get a better representation or a formalization for this. Well, all we can do is we can have, say, integral from T0 to T plus delta of t dt, which is equal to 1 when, again, T0, or let's say 0, is in T minus and T plus, and 0 otherwise. If 0 is not, t is equal to 0 is not in that range of integration at least. And this is the definition of the Dirac Delta function. It's not actually a function, it's actually a distribution. I will discuss a little more about this in a few minutes. So this is the definition of Dirac Delta function, and we can represent the force by just Dirac delta. So delta m naught v and Dirac delta of t minus t naught, because we have instead of 0 we have the point where it's non-zero, the function is non-zero, at t naught. So we have to basically shift the input of the delta function. And if you plug this into an integral like the one I've starred up here, we're going to get exactly what we intended it to be, because it's going to be 1 when t naught is in the range, and 1 times delta m naught v is just delta m naught v. It's going to be 0 if t naught is not in the range, which again 0 times delta m naught v is 0. So the way I like to think about this is a continuous version of the Kronecker delta function in your subscript summation convention. Because if this Dirac delta was 1 when I was equal to j and it was 0 otherwise. So analogous to that, I would not say exactly similar to that, analogous to that, if the argument the 0 of the delta, because we can even have a t squared minus 2, in which case we'll have two sort of piecewise cases going on. But when the argument of the delta is equal to 0, that's when the delta is going to integrate out to give us 1. Otherwise it's going to give us 0. So it's sort of like analogous to that. When I is equal to j, think of ij as like the arguments of the Kronecker delta. In this case, arguments or the continuous analog of subscripts is arguments. This is basically elements of infinite dimensional vector spaces, Hilbert spaces and stuff like that. It's a really detailed theory. You can check it out in some mathematical physics textbook. But it clearly, this statement is pretty warranted. It's pretty justified if you think of these as continuous functions, continuous versions. Okay, so let me give you a real solid example of where Dirac delta functions are used. Well, think of density. There's many types of densities. There's mass density, which is classical, or just when you don't specify anything, that's what density is. There's charge density. You can also have current density. Many types of densities. Main ones that we focus on, at least what I'm going to do on this page, is mass density. You can look into charge densities, current densities. I mean, if you want to, it's not really that useful. Well, we always, in equations, in whatever equations you're using, and when I mean equations, this is again applied math / physics department going on. We use this for like continuum mechanics when we want to analyze fluid flow. We want to analyze fluid flows and like stuff that is continuous, basically, not discrete stuff you have to integrate, not sum over. In which case mass is always given by a triple integral of the density, the mass density, a scalar field. This is always true. That's why you get the entire idea of integral equations. So density is really important. You can sort of categorize an entire system based on how the masses are distributed, and that's what density is. It's a measure of mass distribution, how dense an object is with infinitesimal mass elements, and or how sparse it is in terms of packing, at least. I mean, you can do this for like a big continuous, like a large body. You can also do it for point masses, point object. What I mean by a point object, just let me clarify this, is some finite mass sort of packed in one point exactly. So we kind of sketch it out. Consider sort of just one dimensional case for now. This is the origin, this is your x-axis. Well, at the origin, remember the sort of the spike up we had for the ideal impulse force versus time graph case? We basically have that for this guy. I'm graphing density, mass density, or in this case it will be linear mass density with respect to sort of length or a spatial coordinate. But the area of this entire thing, say from negative infinity to infinity, is going to be 1, and this is for a unit mass. We can of course, you know, add a factor and get the mass we want. So in order to represent something like a point mass, we actually need the Dirac Delta function, because you know it's one of those hypothetical cases of an infinite sort of spike at just one localized point. It's not like it's like different values everywhere else, and like infinite at just blowing up at one point where there's sort of a bad point or something. It's just localized, just one spike with finite area. So this finite area actually constrains us, otherwise it could have just been a divergent value, a divergent function. Well, a point mass in 3D, in three-dimensional space, call this the z-axis, the y-axis, x-axis. So your point mass is like localized mass distribution m naught at the origin, say for example, at one given point. Remember that. So this is kind of what it looks like, and the density of this system is what I've graphed on top. Again, this is sort of density in linear density, but I think you see the idea here. So whenever stuff looks like this, with sort of this infinite spike going at one single point but with a finite area, you know you have to use the Dirac Delta function. Okay, so for a point mass, say m naught, way we can represent this is, consider this sort of volume integral. So this entire space, or the at least a concerned an important subset of R3, is what I'm gonna call V. Could be improper subset. So the volume integral of mass density, which is a scalar field, gives you the total mass in space V. So say for given space V, do a volume integral. We want this equal to m naught, right? So if I write this sort of in a case-wise manner, we wanted m naught when the origin belongs to region V. It's 0 otherwise. Makes sense, right? Because the origin was the singular point where the point mass was. So the way to do this, the way I'm gonna show you now, is write the density function as m naught times delta x, delta y, delta z. Instead of having just one delta t, for example, like the last page, I'm gonna have 3 deltas, because if you sort of integrate, do the volume integral of this entire thing, in Cartesian space you have dx, dy, dz with appropriate upper and lower bounds. You can do that with parameterization. M naught, delta x, delta y, and delta z. If you basically, do the triple integral properly, take the delta x with the dx, integrate it. If 0 is included, you get a 1. If x equals 0 is included, you get 1 for the x integral. If y equals 0 is equal to, if y equals 0 is inside the region, you're gonna get 1 for the y integral. If z equals 0 is in the region, you're gonna get again 1 for this integral, which gives you m naught if 0, 0, 0 is inside the region. If any one of these fails, the entire thing goes to 0, because it's a product of 3 integrals. So we want all delta x, y, and z to be satisfied, because if say one of them is satisfied, you're gonna get, if x equals 0 is satisfied, you still are free to choose any y and z, which is just going to give you a plane in the yz space. And that's the problem with fixing one of them. Fixing 2 of them, you just get a line or a curve, and fixing all 3 of them, you get a point. So you want a point for a point charge, so we want all 3 of them to be satisfied. Let me generalize this notion. If we have a point mass at the point x naught, y naught, z naught, we again shift like I did in the previous page from t equals 0 to t equals t naught. So then it's going to look like m naught delta x minus x naught, delta y minus y naught, delta z minus z naught. Okay, so again, I remember what I said. Well, the Dirac delta is not, mathematically speaking, a function. It is rather a distribution. And this again sort of manifests in the fact that deltas should not exist outside integrals. And the fact this sort of quoted fact is evident because if you look at the graph of the density function in the previous page, there was just one sort of say infinite spike at 0, and we could only really do something about it because the area under it, this entire thing was 1. This area thing, and I had boxed it up, was a really important criteria. Well, and this area was again the fact that you integrate Dirac delta on an appropriate interval. You get 1 if, say, t naught is in that interval. 0 otherwise. So again, this area equals 1 was highlighted in the fact that the integral is 1. The Dirac delta on its own is just this spike, this infinite spike, which is basically an infinity. So it makes sense that they shouldn't exist outside integrals because they're just infinities. But what we can do is we can write them as sort of sequences, and that's because, let me just first, before doing that, let me kind of try to give you an idea of what a distribution is. Okay, so a distribution in mathematical formalism, distributions are generalizations of regular functions, say, that they teach you before starting calculus, that make, say, differentiation and integration possible when you can't do it on the function itself. So you can perform these operations on the generalization of the function, which is the distribution, when you can't do it on the function itself. So think of these as sort of extensions to functions, or whatever functions do. So a function acts on points in the domain. So instead of acting on domain points like functions, they act on test functions. And test functions are basically infinitely differentiable complex functions or actually what test functions means is functions with compact support, which are infinitely differentiable. So test functions which are infinitely differentiable, which are complex, and test functions are functions with compact support. Now what support is, compact because of Bolzano-Weierstrass, Hein-Borel, is closed and bounded. Support is are basically subsets in the domain of a function where the function is non-zero. It's zero everywhere else. Okay, this is really bad, dry, pure mathematical jargon. But what the idea is, and what I like to do is I like to give a linguistics analogy. Is what I mean by generalization of functions. Think of this the distributions idea of generalization of functions as the Proto-Indo-European root. It's not really a language; it's a root. Because the way when I think about it is what I mean by these test functions or the sort of the counterpart for these domain points, when if you use this analogy, test functions are just gonna be those basic sounds that are sort of bestial in nature, which form the basis of Proto-Indo-European. Because I call it the Proto-Indo-European root because it's not really a language. The words aren't really fixed. They're just a bunch of like phonetics for phonetical structures that certain languages like Sanskrit, Russian have used. And those sort of the basic elements of those phonetical structures are basically those basic sounds. Pure sounds, not even alphabets like A, B, C, or like even like or something more sophisticated or structured, some like just cries that animals make, like ah, oo, e, stuff like that. All possible sounds you can make, allegedly. So I'm not sure if this helped, but for all of you intrepid linguistics aficionados, this might be an interesting point to sort of ponder upon. So food for thought in any case. So as I said, deltas should not exist outside integrals, but what we can do is we can express them as sequences, delta sequences, which in the limit that some parameter, some variable goes to infinity, they become the delta function. So something like this. So delta of t is just limit as n goes to infinity, delta sub n of t. So this is a delta sequence which approaches or sort of converges upon Dirac delta. There's many ways of doing this, or the many ways of finding such sequences. One of them is as follows. Delta sub n of t is piecewise. N, if minus 1 over 2n is less than t, which is less than positive 1 over 2n, and 0 otherwise. So it's giving you this sort of range. And sort of one thing that's pretty clear is the integral of this guy is 1. Like, despite the fact that you take the limit as n goes to infinity or not, but anyway, but if you take the limit as n goes to infinity, you can see the n, the height goes to infinity, and this sort of range for t is sort of shrinks down to 0. Let me actually try to construct a graph for this. So again, I'm trying my best to draw here. So what it's going to look like, say for delta sub 1, it's going to look a little like this. Something like this. This is say negative 1/2, plug in n equals 1 with a height of, well, 1, and then this is delta sub 1 of t. I'm just gonna draw some terms of the sequence. Then we have something like this, negative 1/4, height of 2, delta sub 2, and then we have something like this, negative 1/6, delta sub 3 of t with a height of 3. So this is what it looks like, and then you have this sequence, and again, if you take the limit as n goes to infinity, this base comes closer and the height increases because we're trying to maintain constant area of 1. So this is kind of what it looks like. Okay, there's another ways of doing this also. This is just one type. Another way of doing it is, write it as number 2, what I call resonance. So you have delta sub n of t is equal to n over pi divided by 1 plus n squared t squared. So this sort of exploits the fact that the integral of this thing is going to give you an arc tangent from negative infinity to infinity, which will just be pi, and divided by n, of course. And the graph of this, let me try to sketch something here. It's going to kind of look like this. Kind of looking like this. So this 0 point, this t is equal to 0 value basically. This is the t-axis, didn't specify that. This is delta sub n of t. Well, this t equals 0 point, the value at that is n over pi. You can verify it plugging that value in here. And when t equals 1 over n, you're gonna have half of this height. It's gonna be over here. So this t value is going to be negative 1/2, 1 over n, and 1 over n for, say, n over 2 pi. That's just one interesting property of this guy. And again, all of these, what holds true is the limit as n goes to infinity, you get the Dirac delta. You can clearly see this with this case. It's just going to peak up. Another way of doing it, calling it number 3, is using the Gaussian. Yes, Gaussians, we love Gaussians, don't we? So delta sub n of t is equal to n over square root of pi e to the negative h squared t squared. And this again exploits the fact that the Gaussian integral is basically going to give you square root pi over n from negative infinity to infinity. I have made an entire playlist on the Gaussian integral, so please check that out. Okay, let me quickly sketch this. Shouldn't be too hard. It should look similar to the one on top, because a Gaussian is actually a sort of a bell curve. So let me just sort of do an exaggerated version of that. Something like that. Again, this asymptotically goes to 0. This is delta sub n of t. This is t. T equals 0, you're going to have n over square root of pi. You can clearly see that plugging stuff in. If you plug in t is equals to 1 over n, well, you're going to have a 1 over e times n over square root pi. So 1 over e times or square root pi. That's the y value for 1 over n, and same thing for negative 1 over n. So if you take the limit, you sort of see this peaking out, pretty similar to the resonance, the inverse tangent case. Okay, so Another way of doing it is using what we call the sinc squared function. So this delta sequence is going to look like, say, sine squared of nt divided by n pi t squared. So you see there's a sine squared of the argument divided by the argument squared, and again this is one of the integrals I believe is on my channel. Check that out. You can do this using some complex analysis, Cauchy principal value, which of course I will be covering in this in this sort of playlist streak after delta functions, that is. Okay, so let me try to graph it again. So we're here. So now this, since we have a sine squared, we're going to have these positive oscillations. I'm trying to smooth stuff a little bit. This is t. So at t equals 0, well, the function actually doesn't exist. The limit exists, and it is precisely n over pi at t equals 0. And I know you can take literally any other point, say 1 over n or something, and you can probably see it go to 0 at those points. So you can take this and this. Again, this is a really bad drawing, don't really refer to it, but I just wanted to emphasize that we have these Wrigley oscillations which sort of get lesser and lesser, or to say it, more and more insignificant, more and more inconspicuous as we increase n to infinity. One final way of doing it is using the sinc function, which is basically sort of the unsquared version of this. So delta sub n of t is sine of nt over pi t, which I believe is the Dirichlet integral. I've again made videos on this. It exploits the fact that this guy will be pi irrespective of n. So we just need n in one place, not like in two places here, inside the sign and in the denominator, or even here. That's one advantage of using the sinc. But what's a little peculiar about this, and which wasn't evident in the other guys, is that when I draw it out, it sort of also goes in like the negative region. So personally, I actually like the shape of the sinc function. It sort of goes in these negative regions. So you might say, well, what's the big deal here? Because say this is 0 point. That happens when you have negative pi over n and pi over n, and n over pi for t equals 0 in the limit. Well, if you take limit as n goes to infinity, this sort of base, it comes closer and closer, height increases. What about these oscillations? They won't really change. They're gonna be there. They're gonna look again pretty inconspicuous, just like this with the sinc square, but they're still gonna be there. I mean, there's gonna be some stuff in like the negative axis. What do we do with that? Well, remember the definition of the Dirac delta function. So we wanted a Dirac delta function. The definition of the Dirac delta function was precisely this, that it was 1 when the 0 of the argument was in the range and 0 otherwise. That was just the definition. This was the definition. If a function satisfies this property, you can classify it as a Dirac delta function. And if you do this, for our case, say dt limit n goes to infinity sine nt over pi t. Well, you're going to get just 1 when 0 is in the range and 0 otherwise. So since it clearly satisfies the definition, this is a delta sequence. This delta sub n is a delta sequence. So the takeaway from this, the last delta sequence, is that the Dirac delta is a title. So if anything, a general function, a non-elementary function, or I don't know, something like that satisfies the definition of the Dirac delta function, then it is a Dirac delta function. It's not, there's no the Dirac delta function, it's everything's like a Dirac delta function. That's what I'm actually trying to show you here, that it's just a title that a function, a special function, or an object can take if it satisfies this property that I'm basically starring up. So it's not about the shape, because we have these oscillations going on that, like, like in the negative axis also, negative t also, that none of these other guys had. I mean, this had a little oscillation, but these other guys, they didn't really have those. Like the first guy, like absolutely no curvature. That's how we define these squares, these rectangles. So before ending this video, I would just like to introduce one property. So integral from t minus t plus delta t minus t naught of some function dt, so product of Dirac delta and the function, is going to give you the function evaluated at the 0 of the Dirac delta if that 0 of the Dirac delta is in the range and 0 otherwise. Okay, so, and this is under the assumption that f of t is continuous and well behaved, at least in this range. This is what I call, is commonly called, the shifting operation. This is the continuous analog of contracting over indices. So, you know, stuff like this. Or is AI? It's sort of like that, because you're choosing that value where it's the Dirac delta is 0, or where the Dirac delta sort of spikes up, and you put that, basically changing those, the initial argument, the general variable of integration, to a specific one, which is t naught. So let's try to kind of sketch out a proof. It's not the most rigorous one, but it kind of works. So this guy has is 0 everywhere except at t equals t naught, where you saw the graph, it has a spike. So what we can do, since it's 0 everywhere, we can sort of break down our integral from, say, t minus to some some point that's like off by t naught by some arbitrarily small value epsilon. So for some epsilon greater than 0, which is arbitrarily small, plus t naught minus epsilon, because we want to cover this entire range, we want to maintain this equality. T naught plus epsilon dt delta t minus t naught f of t, plus do it with the t naught plus epsilon t plus dt t minus t naught f of t. Since the Dirac delta is 0 at all points except as t equal to t naught, this will go to 0, so will this go to 0. We will retain this because this is like infinitesimally small neighborhood of that of t naught, and sort of this is an idea from a real analysis of using epsilons and constructing these neighborhoods. For those of you guys that don't really have or don't really formally know an analysis, it's fine, just go with it. It's sort of shouldn't be that hard to understand. Just it's sort of like the assumption that limit as epsilon goes to 0 going on here. This is an analog to contour deformation from I think my video on complex analysis, so check that out if you haven't. There will be more complex analysis videos in the future for sure. Okay, moving on ahead. Since we know f of t is continuous, it is constant for this integration from t naught minus epsilon to t naught plus epsilon. Is going to be a constant f of t naught. And again, the idea of using epsilons and like taking a small neighborhood is sort of comes in handy because the definition of continuity using epsilons and deltas sort of connects with this use of epsilon here. So the epsilon delta from continuity sort of ties in here, and where epsilon is represented that arbitrarily small value which was greater than 0. So using that and the continuity of f of t, we can directly plug it out of this integral. So you get f of t naught because it's a constant dt delta t minus t naught, and since this is 1 for t naught, the integration, that's just the definition of the Dirac delta, you just get f of t naught. So this is a rough way of sort of proving it. Oh, and by the way, let me just clarify one thing quickly. Writing dt in before sort of the function of integration is a physicist notation because we're thinking of integrals as operators, integral operators, and this again connects back to operators, a video on operators in a Cartesian coordinate system or orthogonal coordinate system. Mathematician's convention is writing the dt after. You can choose either, it doesn't matter. This is basically a topic in applied math or mathematical physics. So I believe this is all for this video. I hope I wasn't too fast. If I was, there's always other videos who explain in a different way, or you can just sort of rewind this video or whatever. But yep, I hope you enjoyed. Please like, share, and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Digamma in the math community. In the meantime, stay home, stay safe, and peace out. Stay tuned for more content.